Hey friends, just a note, this is actually one of the first episodes Connie and I ever recorded together many months ago. We've been holding on to it for a rainy day and it's been pouring lately. So this is one of our experiments. Heads up, we hadn't quite figured out Connie's audio setup yet, so she does sound a little fuzzy, but it's still a good conversation, so I hope you enjoy. Hello, and welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but still want to be its friend.
I'm your host, Connie, and I am a writer, pop culture enthusiast, and bestie to Moiya and the universe.
And I'm Dr. Moiya McTier, and I'm an astrophysicist, a folklorist, and a good friend to the universe. I was on the phone with the universe for like 3 hours yesterday.
Wow.
Connie, what are you drinking or snacking on?
I'm having some peach cobbler and ice cream.
Out in this field?
Yeah.
Okay.
Yeah.
Did you warm it up on the fire?
Of course.
Yeah, I saw
got
you
my
do
little
it.
ice, my little cooler for my ice cream, just a little small cup. I don't need too much, but it's really warm out here, so I thought it would be a nice accoutrement to our evening.
Lovely. Yeah, it is very warm by the fire. I have some cheese and bread, I guess a grilled cheese. I'm doing a grilled cheese on the coals of the fire.
Delicious. Very cozy.
So while that is cooking on the coals, we're going to be talking about the Fermi telescope, the Fermi Gamma Ray Space Telescope, as it's formally
Its
named.
government name.
Yes,
Yeah.
exactly.
Well, what do we call it in the streets?
Fermi.
Okay.
Fermi, if you have like a
Fermi.
accent,
Okay.
I guess, because he's Italian.
All right.
Have you ever heard of this telescope before?
No. I haven't heard of Fermi or the telescope or the Fermi telescope, so I'm excited to learn more.
Yeah, okay, great. So Fermi is a gamma ray telescope, and I think you probably aren't alone. There are probably many people who haven't heard of Fermi, like most, because gamma ray telescopes do not get the attention that the other telescopes and other wavelengths get.
Do they need a better PR team? Should people know more about these kind of telescopes?
I mean, it would be nice if people knew about all kinds of space stuff.
True.
But I don't know. I'm not a gamma ray girly, so I'm not personally going to be out here in the streets with signs for gamma ray telescopes.
Okay.
But I would love to tell people about it in an episode of Pale Blue Pod.
Okay, let's do it.
Great. There are other gamma ray telescopes that I will talk about in future episodes, but for now, we're going to do Fermi, and I want to give you a little bit of a gamma ray primer because it's
Please?
Yes. Yeah. It is not a type of light that we can see, and as far as most scientists know so far, it is also not a type of radiation that can turn you into a superhero.
Dang it.
I know.
It's fine.
I know.
It's whatever.
Unfortunately. But they are just really energetic photons. They're really energetic wavelengths of light. They have wavelengths less than 10 picometers. 10 picometers is also 0.01 nanometers. It's 1 meter divided by 100 billion. It's really small.
I don't think my brain can compute just the words, much less the concept. So that is really small, yes?
Yes,
Obviously.
yes.
I felt my brain try to shrink into that kind of small space, and it couldn't do it.
It is really small. It's on atomic scales. Actually, gamma rays are so small that you can't capture or reflect them with mirrors because their wavelengths are smaller than the distances between atoms in the like material of the detector. It would just pass right through the material. So the way we need to detect them is by having the gamma rays pass through a really dense material. It'll interact with the electrons that are hanging out on the outsides of those atoms, and it'll what we call Compton scatter away. So it'll like glance off of the electron.
Sounds like a basketball move. It'll just go right off and then right into the basket. Yeah.
It's the alley-oop of the atomic world. So they bounce off of the electron and they lose some energy in that collision. So they are now a lower energy photon, but another type of charged particle also gets produced through those interactions. And we can detect those charged particles and measure their energy and where they came from in the array of the detector. And in that way, recreate a gamma ray image.
Oh, so really, it's like not the ghost or the shadow, but like we're not catching the thing, but the things around the thing.
The things that the thing makes.
Oh, I'm sorry. Okay, so the things that the thing is producing, the energy. So that's what we're able to capture.
Yes, we capture the charged particles that are created in that collision. And because the gamma ray comes in with so much energy, those particles that are produced, they keep moving in that same direction. So they keep going through the detector, the gamma ray detector, and they hit another type of instrument that can measure the energy in that charged particle.
Sounds like a lot. You say it can't be captured by mirrors, but it sounds like a lot of reflection.
No, not reflection.
No. Okay.
It's passing through objects and colliding with things and then bouncing off on like the quantum level, bouncing off with lower energy in like a different form, technically.
Okay.
And so we are not detecting a gamma ray photon. We might get some lower energy photons, but we still aren't even detecting those. We are detecting the electrons and positrons that are produced through the high energy collisions with gamma ray photons.
Wow.
Yes. So they're really high energy. They are only produced by the hottest, most energetic objects in space, like neutron stars, pulsars, big black holes, supernova explosions. And because they're so energetic, we don't even use the same units in gamma ray astronomy that we use in other wavelengths of light. So if you're talking about optical astronomy, like the type of light that you can see, you're probably going to hear numbers in terms of wavelengths. We say 650 nanometers. That is the wavelength of light, the distance between the two peaks of the light wave. If you're a radio astronomer, you might be more likely to talk in terms of frequencies, the 1420 megahertz line, for example.
Yeah.
In gamma ray astronomy, they talk in terms of electron volts. It's a direct measure of the amount of energy and not like any physical property of the light wave itself, but more of a measure of energy for that light particle. Because light is weird. It behaves as both a particle and a wave. And scientists have studied that relationship a lot. There is a relation called the Planck equation, and it lets you calculate the energy of a photon as long as you have its wavelength or its frequency. So the energy is the Planck constant. It's this value that he measured, so we don't have to.
Okay, great. Thank you, Mr.
Someone
Planck.
measured it, yeah. And so the energy of the photon is the Planck constant times the frequency of the light, or the Planck constant times the speed of light over the wavelength of the light, because that's another way. Like you can really just kind of play algebra with these and swap variables in and out as long as you know how they're related.
Well, yeah.
I did say play algebra.
I need you to know that I've never played algebra.
I did say that, yeah.
It's okay. It's okay. And that's why I'm here to learn.
Because my mom and I used to play algebra in the car when I was little. When I was a young, like 4 or 5-year-old in the car getting bored, we would play the X game, which I later learned was algebra.
Wow, she tricked you into learning
Not
math.
tricked.
No.
No. I asked her because I was bored.
I'm sorry, I forgot who I was talking to.
Play algebra.
I never played the algebra game, but I know the people who came up with this equation. That's what they did. That's how you have to do it in order to come up with those letters and symbols over there.
Yes.
Just imagine the GIF where like all the numbers just pass over my head, but you are up top and like somehow you're like sorting through them. I don't know.
Oh, I like that. I like that imagery.
Yeah.
Okay, so that's my gamma ray primer.
Okay.
If anything else about gamma rays comes up throughout the episode, please let me know.
Okay, questions. Yes.
Yeah.
Okay. So we want to use this information for what?
To study the universe in gamma ray wavelengths, because different objects in space will show different characteristics if you look at them in different wavelengths. If you look at the optical wavelengths, you're going to see the stars and the galaxies the way we do with our eyes. If you look in...
And where the color is how we perceive them.
Yeah,
so it's like white lights in the dark sky.
Well, white is really the combination of all of the visual colors. But yes, it would pretty much look the way that it would look to our eyes, removing any sort of filtering through the atmosphere or whatever. Then if you were to look in the ultraviolet, it's going to be really bright at the centers of galaxies, but because you're looking at stars in a different wavelength, they just look different. Like the best analogy I've ever heard is that each wavelength of light is like a different instrument in a symphony, and you wouldn't want to hear an orchestra that's just played by flutes or just played by bassoons. You need all of the instruments because it sounds different.
But you could like look at an orchestra and like isolate a particular instrument just to hear what they are playing. Yeah. Maybe with more clarity and with more, maybe precision or critical ear.
Exactly. Yeah. So if looking at the universe through radio waves is like hearing the contrabassoons, then looking in the gamma ray is like only listening to the piccolos. But you need to hear, you need to hear both to make sure that everything is like coherent.
Yeah, and they all play together in the grand orchestra that is the universe.
Yes. And so we had already launched some gamma ray telescopes into space before, like worldwide. This was not the first. But after we launched the Compton Observatory, named for the person who discovered like Compton scattering. After we launched that in 1991, we immediately saw that there actually was a lot of interesting stuff in the gamma ray sky. Things that shine brightly in gamma rays are like pulsars and black holes and really, really massive bright stars, dead stars that are merging into each other. Those are the types of things you can see really brightly in the gamma rays. There's also kind of just like ambient gamma ray noise around the universe that we didn't expect to be there. But we saw it in 1991. So in 1992, a group of astronomers and high-energy astrophysicists got together to start planning the next mission. Compton lasted until 2000. So they really got started with its successor almost immediately after it launched.
Wow.
And for 16 years, they were designing, they were planning, they were searching for funding, which I think they had a hard time with because it ended up being a massive international collaboration between the US, France, Italy, Japan, and Sweden. Fermi is now officially a CERN experiment, like the people with the Large Hadron Collider.
Ah. And it's because each country's scientists needed, is it more funding? Is it like convincing people to fund it because it's something that is hard to explain or people are not understanding it or just like not funding science? Is there a particular reason why every country, is it just really expensive to build?
These types of telescopes are usually big international collaborations.
Okay, that's the typical. Okay,
yeah,
that makes sense.
Especially if it's not, NASA has some observatories that they call grand observatories that they like spent a lot of money building back when NASA was really well funded. And Compton was one of the great observatories.
Okay.
And after that, I think immediately after, people were like, we just launched a gamma ray telescope. We're not going to give you a bunch of money to make another one.
Right.
But other countries had not just launched a gamma ray telescope, so they were more inclined to add some funding.
Gotcha. Okay.
But NASA and the Department of Energy were the two groups in the U.S. that were involved with Fermi.
Gotcha.
So the planning started in 1992, and I really couldn't find a lot of documentation about their planning. Usually I can find like initial specs or a timeline of initial meetings, and I couldn't find that at all. Initially it was called, and until it launched, it was called the Gamma Ray Large Area Space Telescope, or GLAST. That was its official acronym, but it was renamed after it launched for Enrico Fermi. So it launched in June of 2008 from Cape Canaveral in Florida on a Delta II rocket, for those of you who are interested. But it was renamed in August of 2008 for Enrico Fermi, who is an Italian high-energy particle physicist.
Was he a high-energy guy? I feel like I have to ask.
Yeah, actually, yeah. So he was well known. He had a reputation for asking kind of like open-ended, big philosophical or like difficult theoretical questions to his colleagues and his students and people around him. And the most famous example of this, like definitely, I think in his mind, not one that would have stuck out as an interesting question, is that in 1950, when he was visiting Los Alamos Labs in New Mexico, he was walking to lunch with a few of his colleagues and talking about flying saucers, which were getting more popular in the media around the time. Yeah. And he just kind of, in a throwaway line, asked his colleagues, like, where is everybody? Where are all the aliens? And that got picked up by Carl Sagan in 1963, when Sagan was talking about aliens and the search for extraterrestrial intelligence. And ever since then, the Fermi paradox has been this like open discussion. Scientists don't really talk about it anymore, but every time I give a talk, someone asks me about the Fermi paradox. Like, the internet really likes the Fermi paradox.
Sure. We do love to wonder where the aliens are. So
yes. And there are many different proposed solutions to the Fermi paradox. The real answer, and if you ever see me give a talk and someone asks the question, this is the answer I will give, is that there is no paradox at all. We just haven't explored space enough to give a definitive answer. Honestly, this whole Fermi paradox thing is like if you ask a guy to go get you a specific medicine from the medicine cabinet and they come back and they're like, it's not there. And they like didn't even open the medicine cabinet. They looked on the shelf below it.
You have to go look for data because it's like, well, I don't know if you looked everywhere. So I'm going to look because you can't have looked everywhere because I know they're in there.
Right. Yeah. The Fermi paradox is just weaponized incompetence from a bunch of bros who are interested in space.
Okay. Yeah.
That's the very harsh way of putting it. But no, the real answer is that we just haven't explored enough. You know,
we always need more data.
Yes, we've only been actively trying to interpret these signals for 65 years, and we've only been emitting signals for like a century. And it's that space is bigger than 60 and 100 light years wide.
Yeah, the information is coming in. We just need more money to do the research for it.
I mean, yes, but like literally not even more money, just like more time. Like space is big.
Yeah, of course. Yeah, it's not just about the information coming in. It's just look over here. There's infinite space to look.
There's infinite space to look, but also there's infinite space for this information to have to travel. Like I'm saying, no matter what direction we look in, space is three-dimensional, so we can't look far enough yet necessarily.
Yeah.
Yes, so it was renamed that after it was launched through a public contest that NASA ran.
I was going to ask, like, why, if they already had, is the original name part of it at all, or did they like completely like get rid of it?
Completely
it's
changed
not like
the name.
The Fermi, telescope, but like, has like a subtitle.
Well, I mean, the original title was generic, which is why they wanted to change it in the first place. They were like, the Gamma Ray Large Area Space Telescope just isn't grand enough for what we want this instrument to do. And so they held up a public vote, and the public wanted to honor Enrico Fermi, who must have died before that. They don't name telescopes after living people. And so they changed it to that because it was just more impressive.
Yeah.
Initially, not that I could find much information about their first plans, but it seemed like from early conversations, they were interested in having a telescope with a large field of view so that it could see much of the sky at once, and have a big collecting area so that it would be able to see kind of faint things or objects far away. They wanted it to survey the whole sky, and that is what it does now.
Wow. Now, telescopes have to be really large, right? Like, I grew up thinking about a telescope you have in your backyard or whatever, but the amount of information that it needs to obtain means that these things have to be really huge, right? How big is this one?
We don't process the data in space. It's not like we need data centers in space. They send the data down to us.
Oh,
they don't.
Okay.
Yeah, they don't need computers up there doing the data analysis. The instrument sends data down. Fermi sends data down about 6 to 8 times a day, and then all of the data is processed here on Earth.
I'm sorry. Fermi, the telescope, is in space? Have I missed that part this whole time?
It launched in June of 2008.
So when you say launched, I thought it just meant they launched it. It was the grand opening. They opened the doors, and they are now studying science there at a telescope observatory place.
Damn hermeneutics. They get us again. No, when I say launch, I mean a rocket launch.
Okay, got it.
We're learning.
We're learning. This is why I'm here.
Hey friends, it's me. Connie went to go get some more ice cream and grilled cheese ingredients so we could re-up on our snacks, but I figured I would use this opportunity to share some messages with you. The first being a thank you to the patrons who support this show financially every single month. We really would have a hard time making this show without you. We're an independent podcast, so we don't have big companies backing us, and to have the support of our listeners just means the world to us, so thank you so much. And we want to give a special shout out to our Sun-like stars, Scott Reynolds, Tom T., Nicole Bartlett, Ashley Shambo, and Bruce Sedloff. Thank you from the bottom of my heart. You're golden, and I really appreciate you holding down our Pale Blue Pod's stellar system. If you would like to support this indie podcast on Patreon, you can hear your name on the show, make it onto the patron star chart, and get research notes for most episodes by joining at patreon.com/palebluepod. That's for $5 a month. It's a little bit more than $1 per episode. If a monthly donation is not something you're into, you can make a one-time donation and become a supernova in the Pale Blue Pod sky at the PayPal link in the episode description. Of course, if you can't support the show financially, we understand. Things are hard and weird, and sometimes it's just not the right time. So if you would like another way to help out Pale Blue Pod, the best way to do that is to get more people listening to it. So if you can rate and review us on whatever podcast platform you use, or if you could share the episode with someone who you think would enjoy it, someone who has maybe talked to you about the Fermi paradox, or has never heard about a gamma ray in their life outside of comic books, and you think they might want to know the science of it, send it to them, and I will appreciate it, and so will they, honestly. My next message is about Multitude. That's the podcast collective that Pale Blue Pod is a part of, and that my other podcast, Exolore, was a part of. And if you like Pale Blue Pod, there are other amazing shows on Multitude, like Tiny Matters, American Medieval, things that can make you smarter and let you have a good time. And all of those shows are awesome. And if you want to support all of those shows that Multitude gets to do, then you can do that by joining the Multicrew. This is our membership program where we release weird, cool podcasts with new combinations of Multitude hosts, and we share behind-the-scenes details on making our shows, and we have exclusive monthly hangout sessions with you, the Multicrew members, and us, the hosts. So you can see me sitting on my couch in front of my plants, and we play like trivia sometimes. It's fun. You can get exclusive access to stuff like the entire back catalog of our friendly debate show, Head, Heart, Gut, which I often won. And, I just enjoy debating. So now, if you're like, wow, I want to sign up for the Multicrew, but it's so annoying to sign up for new accounts and go to this website, blah, blah, blah. I have great news for you. You can actually enjoy our bonus Multicrew podcasts right in Apple Podcasts. So if you search for Multicrew podcast, you can click join now and then join the Multicrew from there. So that makes it a little bit easier for you if you want to support the Multicrew. Okay, Connie is back with the bread and cheese and ice cream. I'm so excited to have another little nibble, and then we can keep talking about the Fermi telescope. So this is the first imaging gamma-ray observatory in space. The Compton telescope didn't take images. It just, read energy levels. But the public wants to see things. They want to see pretty pictures.
Yes, so, I sure do.
You sure do. And I do, too. That I can tell people about them. I don't care how it looks. I want the numbers. but I know that it's a powerful tool.
Indeed.
So it is an imager, and it has two instruments on it. The primary instrument is called the Large Area Telescope, and it has those detectors that I told you about, where the gamma ray comes through and it hits a very dense object. In this case, it's a layer of tungsten, which is a very dense metal. And as it passes through the tungsten, it hits electrons, and then it produces an electron and positron pair. And then those electrons and positrons continue down into the detector until they hit an instrument called a calorimeter, which, counts calories. And a calorie is a measurement of energy. It is the amount of energy that it takes to heat up a certain volume of water a certain amount, like a certain number of degrees. And so this calorimeter measures the energy in the charged particles that hit it.
Whoa. I did not ever think about the calories in our bodies being related to calories literally anywhere else, honestly. Now that I'm thinking about it, I'm like,
the normies will take a lot of scientific terms for themselves. They do.
Oops. And I just had no idea. I was just out here unawares.
It's literally just a measure of energy, like a unit.
Yeah. Huh. We are space.
We are space. Yes. Oh, I love that. Fermi also has a secondary instrument, and it's called the Gamma Ray Burst Monitor, or GBM, and it has 14 different detectors on it that are called scintillation detectors.
Ooh,
yes. Scintillating.
Okay, but why did they name it that?
they name it that because each detector is based around a crystal that will, it's not quite vibrate, but they will interact. They will scintillate when high energy photons pass through them.
Just like a little finger wave, just like hello.
Yes. Yeah, they get tingles.
Ooh.
They get tingles. And through the tingles, they can translate the high energy gamma rays into lower energy photons that we can detect.
Right.
So they can take gamma rays and translate them into optical light pulses. But different scintillating detectors are going to be tuned to different photon energies. So they have 12 different sodium iodide crystals in the detectors. Those are tuned to the lower energy gamma ray bursts. And then they have 2 that are sensitive to high energy gamma ray bursts, and they are bismuth germanate crystals inside the detectors. I guess I don't know, maybe they're more sturdy or something. So they just only react to the higher energy photons.
I need to see this because it sounds very sci-fi, sci-fi in real life, where it's just I need to see if these crystals are a set piece from a sci-fi movie or if there's something just more boring or more logistical, because I'm just imagining these pillars of crystals and laser lights beaming across them, and it's probably not that cool. Cooler in the fact that it's real science and stuff happening, but
I think it is that cool on a smaller scale. Like, it's not like a bunch of crystals in a big room with light bouncing back and forth between them. Each of these detectors has like a small crystal in it, and they're like, very tiny.
Okay.
Yeah.
Now that I understand that this is not an Earth-based thing, it's like you wouldn't be able to put that in space, except in like a Star Wars. So that's why I was like, from the idea of like a big set piece, but then like a small.
Oh. No, you could hold that type of configuration in a space-based instrument. It would just be expensive and like, on a smaller scale. But you could have that. We just don't, because we don't need that.
We don't need that.
We don't need that. Yeah, it is pretty big. When it launched, it weighed 9,500 pounds.
Oh.
And the whole thing, these two instruments are in a case that's about 8 by 9 by another 8, probably,
feet?
Yes.
Okay.
Yes.
I wasn't sure.
You're right. Units are so important. Yes. Feet.
I was like, how big can it be?
Yes. Good point. Thank you for catching that. So it's decent size. It's a couple people
It's a big boy.
Yeah.
So heavy.
Average.
But it doesn't matter, right?
Oh, it matters.
Okay. So it does matter.
A heavy, it really affects the cost.
How heavy telescopes tend to be. So for me, it's always it's a scale that is heavy. But in comparison to other telescopes, it's a little
average.
Okay.
Yeah. When I saw that weight, I did not have any sort of reaction. It seemed typical.
Okay.
It orbits about 330 miles above the surface, not in a perfectly circular orbit. So sometimes it's a little bit closer, sometimes a little bit further away. And it orbits at an angle, like not perfectly in line with our equator. And it moves fast enough to orbit the Earth 15 times a day, taking like 90-something minutes to do one orbit.
Wow.
Yes.
That's a fast big boy. Average boy.
Average. It's also average speed. The ISS orbits the Earth every 90 minutes.
Oh, yeah. Okay.
Yeah, so these are all average. It's not zipping that fast. I think it's only moving like 8 kilometers per second or something. Yeah. So it's not moving that fast, but it is moving fast enough that it orbits several times a day because it takes a full image of the full sky every day.
Ooh.
Yes.
Do they share that anywhere?
The data is proprietary for a period, and then it can be released to the public, and they keep the data open to the public for at least 5 years.
Okay.
Which is nice. A lot of the observatories do have to make their data public because they're taxpayer funded.
Ah, yes. Please please show us how you are using our money.
Mm-hmm. But there is that proprietary period because a lot of these telescopes have individual scientists or like scientific teams that request data for their own projects. And so you don't want to get scooped if that's the case. Right. So they own the data. And different telescopes have different periods. I think for like the Hubble Space Telescope, you own the data for like a year. And then after that, other people can access it.
Does the data belong to the organization or the individuals? Like I know you get to put your name on it, but does that count as ownership?
You can't copyright facts or data.
True.
So no one
owns it in that, like...
Yes, but some people, at certain times, only few people have access to it. Yeah, you can't copyright facts. These are things I've learned through my work with the campaign, with the Human Artistry campaign. You cannot copyright facts or data, but you can copyright methods and analysis of data. So the papers that people write, analyzing that data, that is copyrightable, and they own that.
And is that what's released, or is it just like the raw?
Both.
Both? Okay.
Well, I mean, so the team that requests the data, they will publish the paper. Or the Fermi team, because of the Fermi collaboration of more than 400 people worldwide, they have published papers. So they own that publication. The data itself is released publicly after a certain time.
Right. Okay. Interesting.
But this originally, when it launched in 2008, it was a survey mission. So it's observing plan was already kind of scheduled out. It was scheduled to last 10 years, 5 to 10 years. And so that's how much science they planned. And now it's going strong at year 17. So they are now taking proposals for observations because you can turn it to specific points in the sky to target a specific object. And it's really useful to turn the telescope to what we call transient objects, which aren't in the sky for a very long time, like a supernova explosion. So you can turn to it. And actually, I have a section later on Fermi discoveries where like that is relevant. So,
okay,
but
great.
most of the time, I think that it's continuing to just take its picture of the sky every day. It is working every day. It downloads data 6 to 8 times every single day.
Wow.
So
Wow.
hopefully we have many years left of Fermi data.
Hopefully. And that 400, that team of 400 is like splitting up, like they're just focusing on all different sorts of elements and writing their papers about it.
That's the whole collaboration. So that also includes the tech people and the like software people, because it does need to be monitored. Sometimes it has near misses with other junk up in space. In 2012, it had to be maneuvered away from a Cold War era Soviet spy satellite. So there are people who are like watching
Stuff's still up there.
Yeah. But there are many people, I'd say of the scientists on the collaboration team, there are still a couple hundred of them, and they will work in teams on a specific question. There will be some people who like find an interesting corner of the data and squirrel it away to write like a 1 or 2 author paper about it. There's so much data that it becomes like a vast sandbox.
Yeah, I imagined that would be overwhelming. The amount of things you have that people would want to know and just study, it's just so much. And that is a lot of data that many times a day. So being able to sort through it to see things that are important is not my cup of tea. That's why the scientists exist.
All of the telescopes have a software pipeline that they develop so you can quickly comb through all of the data that comes down from the telescope. But still, there are whole drives of data that don't get used right away. There are many PhD dissertations worth of data sitting in archives, and there are many PhD students who use that. That's what I used in my research. I never requested my own observations. But it's really nice that it's sitting there for students who come by in the future and need something to work through.
Oh, that's awesome. Because I was thinking it's just like sitting in servers somewhere or whatever. But the fact that there's stuff that still can be used outside of the telescope's initial mission. Is that correct to say?
For many years. The Kepler Space Telescope was officially decommissioned in 2018, and there are still students and like full-fledged astronomers who are combing through its data and confirming the planetary candidates that it found. So the data lasts a lot longer than the initial proprietary period. And they are, in addition to like the initial data pipelines, I know that AI is being used to analyze the data in a more efficient way, which is a use of AI that I support with 90% of my heart.
Yeah, there's always going to be a little bit of always. So
yeah,
makes sense.
It can see 20% of the sky at once, and because its field of view is so large, it actually has to be careful about not getting the Earth in its scope.
The Earth is trying to photobomb, okay? All right? Like, the Earth is just like, there's not enough pictures of me. You guys keep focusing on Venus and Mars. You keep going out to Saturn? No. This thing is right here. Just take my picture.
Gaia is such a diva.
Such a diva.
And sometimes we do. We occasionally will intentionally turn Fermi a little bit towards Earth so that we can calibrate its sensors, because we know how bright Earth is supposed to be in the gamma ray. So we can use it as calibration. But we also can use Fermi to study Earth's atmosphere. I have in my discovery section, which I'm just going to say now because I feel like I need to blow your mind again. I feel like it's been too long since I've blown your mind.
Yeah.
So one of the uses of Fermi is to study the upper atmosphere during thunderstorms, because we have apparently been able to observe that lightning flashes in the upper atmosphere, since it's like really energetic photons that occasionally collide, can produce antimatter in the upper atmosphere of Earth. I've talked about this on the collision episode before, that when you get gamma ray particles colliding in what we call the Bright-Wheeler process, it can produce an electron and a positron, which is the antimatter counterpart to an electron. So lightning flashes can just be up in the atmosphere making antimatter, and Fermi can detect it.
Through the observation of the gamma rays.
Yes.
Wow. I feel like you are trying to deny me a Hulk, and I feel like it's still in the atmosphere. Like, the things are colliding. Electricity is a really powerful superhero tool in terms of like giving powers. So I think if the electricity is going to be passing along gamma, like, we can make this work. Okay.
Okay. Yeah, there's some tardigrade floating in the upper atmosphere that's going to get hit not just by one lightning strike, but two lightning strikes at the same time. And it's going to be that like nexus point of the Bright-Wheeler process, and somehow it's going to become the antimatter particle. All right. Comic book writer, please contact us. We have an idea.
Yeah.
About the range that Fermi observes in. So I said that they're listed in terms of energy. The unit is electron volts. So the optical photons that you and I can see, that our eyes can process, they have an energy of between 2 and 3 electron volts. Fermi observes photons that have 8,000 electron volts at the low end and 300 billion electron volts at the high end.
That's range for sure.
That's range. That's range. It's many decades of range. Decades in the mathematical sense.
No wonder it's like there's not enough data. Like, there's so much.
There's so much. Yes, that's a wide range. So let's get into some of the things it's discovered with that wide range of observing capabilities. It, in 2013, confirmed that cosmic rays, these tiny little energetic particles that we still don't totally understand, that they can be propelled through space and given like a little boost by supernova shock waves. And I love anything that has to do with supernova shock waves, because in my fluid dynamics class in grad school, our professor loved to give us homework problems where we calculated the shock speed of a supernova wave. And it's like the bow shock of a supernova travels so fast, and it also like that same phenomenon generalizes to so many other like Earth-based experiences. And so I feel like I really got to understand Earth better by studying and measuring supernova shock waves.
I love that. We study space, honestly, to learn lots of things about the Earth, and that it was supernova shock waves for you.
Yes.
What is that?
So a supernova is basically a big stellar explosion. And here on Earth, when there's an explosion, the air moves away from that thing in a pressure wave, in a shock wave. The same thing is true in space. Space is more of a vacuum, so there's less stuff to move around. But especially in the areas around stars where supernovae are going off, there's enough gas and dust that there is stuff to push. And these are really powerful explosions, so they push it really quickly, sometimes at speeds that get near the speed of light. And so in 1949, Enrico Fermi suggested for the first time that cosmic rays can get swept up in this supernova shockwave and be carried through space. And that's important because, for a long time before we had good technology to detect gamma rays, it was hard. And so one of the ways that we could do it was through studying cosmic rays. But it's also it's important to be able to see how these different types of particles are associated with each other in these extreme space environments.
Yeah. And like you said, so learn about things on Earth.
Yeah. So that was 2013. That was confirmed for the first time. But in 2024, Fermi found a surprising lack of gamma rays coming from a nearby supernova that had been discovered the year prior in 2023. And gamma rays are a good proxy for cosmic rays because cosmic rays are produced when gamma rays interact with matter. It's another one of those like collision things where the gamma ray photon collides with something and offshoots a lower energy photon and some other tiny particle. Those tiny particles can include cosmic rays. And it was previously thought that about 10% of a supernova's energy goes towards producing and accelerating these cosmic rays. But if you usually see cosmic rays and gamma rays together, we don't see gamma rays here coming from this supernova. Like what is happening?
Oh, okay. So there's a lack where, based on other associations of cosmic rays and gamma rays, you think they should be there, but you're not seeing them.
Right. Yeah. We do not see the gamma rays from this supernova. And we usually can't detect the cosmic rays from a supernova because they will move in all sorts of directions. But the gamma rays could come directly towards us. And they haven't from this supernova for some reason. It's possible that they're being blocked by some sort of debris cloud that absorbs the gamma rays.
Right. Because it would pass through?
Because they pass through objects most of the time. But also because they're so high energy, they don't dissipate as easily as other low energy photons. So they like move on a straighter path farther, like throwing a ball with greater force. It's going to go far straighter.
But then you said there's something blocking
There's something that can absorb it. And so, yes, when gamma rays interact with matter, it can pass right through the space between atoms. But if it does happen to hit one of those atoms, then it can get absorbed or scattered or something. So there might be a cloud of debris between us and this supernova that is, dense enough to be absorbing these gamma rays.
Okay.
But yeah, it's a mystery. There are a lot of mysteries with gamma rays, which I appreciate. And then the last big discovery that I want to talk about is the picture that I know you're looking at. These are called the Fermi bubbles. Can you please describe what you're seeing?
Okay, so there's a black background, and in the center vertical, it's like purple clouds. And in the center, horizontally, there's like a blue, it looks like a blue light all the way across the picture. But then there's like, clouds and wisps emitting from the top and bottom. So it, in a sense, looks like a cross that has a big purple poosh that looks like clouds. Or like a wider wisp, and then the center horizontal image is more like densely packed, but then there's still like the mist emitting from it.
Yes. So what you're seeing is a gamma ray image of the center of our galaxy, and that flat blue line is the Milky Way's plane, like the plane of the disk. So that's where most of the stars are, and so you're seeing really bright beams of gamma rays because that's where the stars and all of like the heavy stuff is. Yes.
So in this image, on this blue line that's horizontal, there's an extra bright spot of white. It looks like white coming through the blue. Is that the sun?
That is the supermassive black hole at the center of our galaxy.
Oh.
Yeah, this is an image of our galaxy, not our solar system.
Oh, it's the whole thing. Okay.
It's the whole thing. Well, not the whole thing. It's the galaxy from our solar system's point of view. So it's like the internal part of the galaxy. Yes. So that bright point of light is Sagittarius A star, which is very energetic and has a lot of gamma radiation swirling around it. And those bubbles that you see, the purple round blobs that extend to the north and south, they are called the Fermi bubbles, discovered in 2010. And they are, each of the bubbles is 25,000 light years tall. So from the top to the bottom is 50,000 light years.
Oh my. That's, I mean, once you kind of see like, oh yeah, it's the plane of the Milky Way. And then and you're like, yeah, that's already a lot of, that's already big. And then these go like plumes plumes above and below.
Yeah, and they're millions of years old. We don't know their origin, but it might be the aftermath of stellar interactions with the supermassive black hole at the center of our galaxy. Maybe it ripped stars, like a really massive star, apart, or maybe several stars collided, or like they became neutron stars that collided, or something. We're not sure. But we've known about this for 15 years. They're very bright in the gamma ray, and the ice cube array in Antarctica. It's this instrument, a detector that's on the ground in Antarctica. It has detected really energetic neutrinos, which is another type of small energetic particle.
Yeah, I was like, they must be tiny. Neutrino.
They're small, yes. They have detected energetic neutrinos coming from the Fermi bubbles that indicate weird atomic behavior going on in the cloud. So, like, this is a mystery. There, like I said, lots of mysteries surrounding gamma rays. But one thing that I think is fascinating about this is that these clouds are moving. It's another shock wave because they are expanding from a central point.
Wow.
And so they are moving at 2 million miles per hour, north and south.
I feel like this entire episode you said numbers that are so large that I'm just like, that's just funny because conceptually I can't understand it, but it makes my brain like try to emulate it, and that makes it like squeeze.
Yeah. And Connie, that is slow. These bubbles are moving slowly through space at 2 million miles per hour. But do not worry.
Just a little jaunt.
They're strolling.
Don't worry about it.
Mm-hmm. They have nary a worry. They're not
the way
rushing.
It looks, I can kind of see that. Like, it's just like, we're just gonna walk over here. Oh, what's that over there? Oh, what's that up there?
Yeah. But you can be the chillest 25,000 light year tall hippie around. If you take a slow meandering step, you're still walking at 2 million miles per hour.
Yeah. Honestly, that's just the way you should learn how to walk in New York City. Like, just get with the program.
Yes. But don't worry, they're not expanding in our direction. They're moving to the north and south of the galactic plane. And we are, like off to the east of the galactic center. So like, we're good. We're fine.
East.
That's where I'll be. That's where someone
That's
will
where
be.
we are. That's where we are.
And that is the last of the Fermi discoveries that I explicitly mentioned. But Fermi's been so great at studying pulsars, the merging of neutron stars and black holes. Oh, in 2017, when LIGO, the Gravitational Wave Observatory, detected 2 neutron stars merging, it was Fermi that discovered the gamma ray burst of light that came from that neutron star merger. And gamma ray bursts are one of the biggest mysteries in astronomy to date. We have detected thousands of them. I think the first detection of a gamma ray burst was in the 1960s. And since then, they're these really powerful events that in a couple of seconds produce more energy than entire supernova explosions.
Whoa.
And like, we don't know why.
Yeah, let's find out why.
So Fermi's been really useful for that. Really, gamma rays, it's like a huge bucket. It's the big bucket of all high energy stuff out in space. And space is such an extreme environment that the most extreme wavelengths are where like the interesting stuff happens.
Of course.
Yeah. That's why I like the radio waves. It's extreme on the other end, the really long, low energy stuff, where instead of seeing these, I mean, honestly, you still see the same things. Like you still see pulsars, you still see black holes and like dust around centers of galaxies. I don't know, but you just get a different sense.
Yeah, a different perspective, a different direction. Not a direction, but like a different perspective.
A different perspective because you are tuning into the less energetic physical properties, which, is just a different way of understanding the universe, and you need both of them.
Honestly, and that's why we're here, because we are cozy and we want to be friends with the universe. And so we're not going out with the universe and partying, okay? Like there are people for that, and you guys have fun. But we are here to study the long, slow path and the slow-moving particles with the universe. This makes sense that this is what you studied. You have built your life around the cozy exploration of the universe, and it sits even in. You want to study the slower things that affect our universe and not the high energy
If by
particles.
slower you mean moving at 2 million miles per hour.
Sure,
yes.
sure. Listen.
Okay, well, listeners,
Anyway.
no matter what is considered slow by you, you are space. Remember that. Bye.
Bye.
Pale Blue Pod is hosted by Dr. Moiya McTier and Connie Gibbs. Moiya created the show with the funny and talented Karine Caputo with help from the Multitude Productions team.
Our theme music is by Evan Johnston, our cover art by Shay McMullen, and our audio editing is handled by the superlative Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Instagram or check out our website, palebluepod.com.
I, Moiya, am Go Astro Mo on all socials.
And I'm @ConStar24 on Instagram.
If you want to support our show, join our community at patreon.com/palebluepod or send this episode to your family and friends group chats.
We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
Thanks for listening to Pale Blue Pod. We'll be back next week.